Okay, let's just dive right into this explainer and demystify the incredible engineering behind experiment number 5, flow through a partial flume. Seriously, if you've ever stared at a rushing canal or a massive irrigation ditch and wondered how on earth anyone measures that sheer volume of water accurately without stopping the flow entirely, well, you are in the exact right place.
So before we actually get into the lab, we've got to ask ourselves a pretty fundamental question. How do engineers measure open channel flow without letting sediment, debris, and rocks just completely trap and ruin the whole measurement system? It's a massive, massive challenge because, let's face it, water in the real world isn't perfectly clean.
All right, here is our roadmap for today. We're going to meet the partial flume, explore its anatomy, dive into the theoretical and submerged math of flow, and finally, look at our lab setup so we can conduct the experiment step by step. Let's get going. Section 1. Meet the partial flume, the engineering hero. Let's introduce the ingenious solution to that initial question. Now, historically, older devices like broad-crested weirs were effective, sure, but they caused high head loss and basically acted like a giant wall. They trapped sediment and created these useless, dead water zones. Then Venturi flumes came along to try and fix that, but they had very small head differences, especially at low Fresnel numbers. That made them incredibly hard to read accurately. Enter the partial flume. This thing was invented to solve both of these massive headaches. It's incredibly accurate, it easily withstands high degrees of submergence downstream, and best of all, it's designed to be totally self-cleaning.
Moving on to Section 2, Anatomy of the Flume. Form follows function. Now that we know why this specific device even exists, let's look at how its highly specific shape actually makes it work.
Notice how the flume here is divided into 3 very distinct parts. On the left, we've got a broad, flat converging section where the water enters. Right in the middle, there's this narrow, downward-sloping throat section. And finally, over on the right, it finishes out with an upward-sloping diverging section. You're going to want to keep this layout in your head because these specific angles are doing literally all the heavy lifting. Because, this isn't just a strange shape for the fun of it. Each angle has a strict physical purpose. That downward-sloping throat artificially increases the head difference between the upstream and critical sections, which makes taking your measurements so much easier and way more accurate. Then, that upward slope at the end produces a high tailwater depth, which cleverly reduces the length of the supercritical flow region. And because this unique geometry essentially forces a high-velocity rush of water straight through the throat, it safely flushes out all that troublesome debris we talked about earlier. It practically takes care of itself. All right, Section 3, the math of flow, calculating theoretical discharge. With the physical shape visualized, let's see how this all builds into the mathematical equations we actually need for the lab. Because the partial flume is an empirically calibrated device, which just means its formulas are derived from rigorous, real-world testing, we calculate the theoretical free-flow discharge, represented by Q, using this wonderfully elegant equation. It's simply a constant, K, multiplied by the upstream head, HA, raised to an exponent n. Now, it looks simple enough, right? But those K and N values are highly specific to your particular equipment. For example, notice how a throat width of a ½ foot has a totally different K and N than a 1-foot flume. In our standard 3-inch laboratory setting, we just use a set formula for theoretical free-flow discharge. Q sub Tf equals 0.1771 times HA raised to the N. Of course, math on a chalkboard is absolutely perfect, but water flowing in a real flume is messy. You've got friction, turbulence, minor imperfections in the material itself. So we bring in the coefficient of discharge, or CD. This is simply the ratio of the actual discharge, QA, which you physically measure with a meter, divided by the theoretical discharge, QTF, which you just calculated. It corrects for those messy real-world variations and tells you exactly how efficient your specific flume really is. Which brings us to Section 4, dealing with submerged flow. The plot twist. We've mastered free flow, but now we've got to introduce a major complication that civil engineers face out in the field all the time. So here is the stark difference between free flow and submerged flow. Free flow happens when the water moves unobstructed, completely free, out of the flume and downstream. But sometimes the downstream water backs up due to channel conditions. When we divide the downstream head, HB, by the upstream head, HA, we get the submergence ratio. If that ratio exceeds 60%, or 0.6, free flow essentially dies, and submerged flow begins. The downstream water is literally choking the flume, and that forces us to mathematically reduce our calculated discharge. To solve this, engineers don't just guess, they use this complex log-log chart to visually locate their exact submergence percentage. By tracking your upstream head on the left vertical axis and intersecting it with your percentage of submergence on these diagonal dashed lines, you can drop down to the bottom horizontal axis to find the exact discharge correction factor. This vital correction factor is known in the equations as QE.
Once you have that QE correction factor pulled from the chart, the math is incredibly straightforward. You simply subtract QE from your original theoretical free flow discharge, QTF. The result is QTS, which is your true corrected submerged discharge. It's really just a remarkably elegant mathematical solution to a very messy real-world hydraulic problem. Okay, Section 5, the lab setup, the virtual workbench. Now that we have absolutely conquered the theory, let's step into the virtual lab and take a good look at the equipment you'll actually be operating. Imagine you're standing right in front of this exact setup in the open channel flow laboratory. Down at the bottom, you've got a large reservoir. A pump pulls water from there, pushing it up through a flow measuring unit, like a water meter, and then it flows directly into our partial flume. Over on the far right, you'll notice a tailgate. Now that tailgate is absolutely crucial because it allows us to artificially back up the water and manually create that submerged flow condition we just learned about.
And finally, Section 6, conducting the experiment, step by step. Let's get our hands dirty and break down the exact procedure you'll follow to run this experiment and collect your data.
First up is the free flow phase. Step 1, you will carefully measure the upstream head HA. Step 2, you'll crunch the numbers using our formula to get your theoretical free flow discharge. Step 3, you literally just read the actual discharge QA straight from the water meter. And step 4, you calculate the free flow coefficient of discharge by comparing your actual reading directly to your theoretical math. Next, we introduce a little chaos, testing submerged flow. You'll close that tailgate slightly to back up the water. Step 1, measure both the upstream head, HA, and the new downstream head, HB. Step 2, calculate your percentage submergence. If it's over that magic 60% threshold, you move right to step 3. Pull out your log-log chart and find your correction factor, QE. Finally, step 4, calculate your corrected submerged discharged QTs and your new submerged coefficient of discharge.
To wrap up the lab, you're going to act as a true scientist and verify the calibration of the flume itself. You will plot your different actual discharges against your upstream heads on log-log paper. When you draw a line through those points, the slope of that line mathematically proves the exponent n value. And once you have the slope for n, you can plug it back into the equation with your data points to mathematically solve for the constant k. You're essentially proving the foundational math from scratch. How cool is that?
Which brings us to our final thought for today. While the Parshall Flume is without a doubt a brilliant engineering hero that solves massive problems with its self-cleaning shape and precise math, the source text notes that it can still become invalid when heavily choked by massive erosion debris in the wildest streams. It's an amazing tool, for sure, but it's not invincible. So it leaves us wondering, if this masterclass of geometry eventually meets its match, what must the next generation of engineers, perhaps some of you watching this explainer, invent next to measure our most chaotic and destructive rivers? Think about it.